general solutions are different to solutions or solving trig functions over fixed domains. So before we did any calculations with fixed domains, it was good practice to think about how many solutions there would be. So like if there was 0 to 2 pi and no period change, then we'd know that there's two solutions. With an n value of 2, well, we'd know there would be 4 solutions between 0 to 2 pi, etc., etc. When we're finding general solutions, what we're doing is finding all the solutions over the maximal domain for each function. Now, that's pretty difficult in this first case to list all of the solutions, because if we look at this problem graphically, what we'd be doing is solving f of x equals sine x, and we wanted to find out, so this would be the same as finding out sine x equal to root 2 on 2. So when is the sine x function equal to the line y equals square root 2 over 2? Okay, and you notice there that it happens really, really often, okay? And it, in fact, happens an infinite number of times in the positive direction and the negative direction. So it's extremely difficult to provide all of the solutions one after another. And what we do is we use a bit of a different way to do it. But notice that this one here requires a general solution because there's no domain provided. This one here has a domain, okay? So this is fixed domain and therefore finite number of sols. There's no domain provided, okay, so there is infinite number of sols. So this is the one here that we're going to need to provide a general solution for. This one here has a finite number of solutions. Now, every year in the methods exam, what I find is a student puts their hand up over a question like this and says, oh, you forgot to list the domain. Okay, you forgot to write the domain, or what domain over which am I supposed to solve this for? And this is implying that you need to solve it over a maximal domain, okay, the set of all real numbers, which means that it's implying that we need a general solution. So the method we use basically is to find particular solutions first and then the general solution by the addition of the period, okay? So let's go ahead and try it out for a couple of examples. So the first up is cosine x equals 0.5. When is cosine x equal to 0.5? So what we do really, girls, is the same that we've been doing in the past, which is we work out our base angles. So when is cosine equal to a half? That base angle is going to be at root pi on, 3. Okay, so pi on 3 is going to give us the cosine value of half. Now what we're also going to note is that, so we're going to say x is equal to pi on 3, that's going to give us an answer. Okay, it's also going to give us an answer down here at x is equal to 5 pi on 3. And now what we're going to do is generate more solutions. So we would say then we could get another solution here. So that's going to be plus, so it's going to be pi on 3 plus 2 pi, all right, which will get us back to this again, and another 2 pi and another 2 pi. So what we're going to do is fit an n value in here. So we're going to say we're going to add 2 pi n, okay, and we're going to do the same for this solution over here. We're going to add 2 pi to get another solution, 2 pi n, where n is an element of z. Now recall that z is just the set of all integers. So z is like -3, -2, -1, 0, 1, 2, 3, 4, ... and ... over here. So it's all of those numbers, okay? So what you're allowed to do is put in for n a number, and what that will do is generate that particular solution. So if you put in 3, it'll generate the third positive solution. In fact, the fourth positive solution, because 0 will generate the first positive solution. All right, now you will find this often written a different way in a textbook, okay? So the one thing to note about the cosine general solution is sometimes you can actually write this with a little bit more pizzazz or style. So notice here that I would go plus pi on 3, but I could also go minus pi on 3 to get this solution here, the negative solution. Or this one here, instead of going 5 pi on 3, I could go negative pi on 3. So what we can actually do is also write this solution as plus or minus pi on 3 plus 2 pi n, where n is an element of z. Okay, now notice that this is exactly the same as this, okay, except the combined solution just is a little bit more aesthetically pleasing. Now this would be full marks, this would be full marks. This shows a little bit more elegance. Do you need to do it? No. Do you need to be able to recognize that this is the same as this? Yes, definitely. And there'll be a link on Firefly to another example, or a VCAR example, where you'll see this particular skill used. All right, let's do this one here. So we're going to go tan 3x is equal to 1 on root 3. All right, so let's grab our base angle, which 1 on root 3 is pi on 6. Our base angle is pi on 6. All right, so what we're going to get is a pi on 6, okay, when it's 1 on root 3. And over here, we're going to get another one, which is going to be at 7 pi on 6. But do you notice that with tan, we're going to generate another solution every pi, all right? So we actually need only one general solution. We don't need two split solutions or a plus or minus with tan, because pi will get us that next solution. So here we go. We're going to say that 3x is equal to pi on 6 plus pi n, okay? Where 0 will give us pi on 6, 1 will give us 7 pi on 6, 2 pi will get us to there, 3 pi, 4 pi, etc., etc. All right, now here is the complicated part. Okay, so now what we're going to do is we have to divide by 3. And what we're going to do is divide both things by 3. So that's going to be x is equal to pi on 18 plus pi n on 3. So what we do now, girls, is that we need to generate further solutions. So this value here will be dilated by a factor of 1/3, but we've also got to dilate the period because the solution happens more often. Okay, so it's going to happen every pi n on 3, right, where n is an element of z. Right, so it's particularly important to note that what we do is dilate the period as well as the first solution. All right, on to this one here. We've got sine x is equal to root 2 on 2. Our base angle is going to be pi on 4 because of that root 2. So when is it going to equal that? So it's going to be there and there. Okay, so at pi on 4 and 3 pi on 4. All right, so we're going to go x is equal to pi on 4 plus 2 pi n, and x is equal to 3 pi on 4 plus 2 pi n. Now notice that we did that nice little move for the plus minus for cosine. It doesn't work for sine, okay? We can't plus minus it because the solutions aren't balanced either side of 0. So here we would maintain these split solutions and say where n is an element of z. All right, this last problem is as hard as it gets. All right, so find this and hence find all the solutions for x in the interval. So they want us to solve this, which means find a gen solution, and then using the general solution, we're going to find all the solutions between negative 2 pi and 2 pi. All right, let's find our general solution first of all. So we're going to solve cosine 2x plus pi on 4 equals root 2 on 2. So that's going to be a base angle of pi on 4. All right, so we've got pi on 4, and over here we're going to go with 7 pi on 4 being the other solution where we're going to be root 2 on 2. So we're going to say this 2x plus pi on 4 equals pi on 4 plus 2 pi n. So there's our first solution. So this one here is pi on 4 plus 2 pi. Now I know I've done a plus minus on one of the previous examples for cosine, and I could do it here, but I'm thinking ahead here and I know something that's going to happen. This translation here is going to break the plus minus situation. So I'm going to list these as two separate solutions. If you want to combine them into one solution, you'll see what happens in a sec. I'm going to go 2x plus pi on 4. The other solution is 7 pi on 4 plus 2 pi n, where n is an element of z. All right, now what we're going to do is we're going to subtract pi on 4 from both sides, or both of these solutions. So I'm going to go with the first one. So this one here is 2x equals pi on 4 removed from pi, this is going to be 0 plus. Now, here's a really complicated thing. So what students will also do is, and because you've been taught whatever you do to the left-hand side, you do to all of the right-hand side, okay? But we're not going to do that in this case, okay? Now this, we're solving for this. We're going to remove pi on 4 from this. We're not going to take it away from the period, okay? So we're not going to take it away from the period because the period is still 2 pi n. All this is a translation, but it's still got the same period at the moment. So this is going to be still 2 pi n. We're going to do it to the next solution as well, which is 2x equals 6 pi on 4 plus 2 pi n. Now I know that that can be simplified, but I'm not finished yet. All right, so now what I'm going to do is now do my dilation, which means I need to dilate the solution and the period. So that's going to be x is equal to pi n, and x is equal to 6 pi over 8 plus pi n, which that one there will be x is equal to 3 pi on 4 plus pi n, okay, and this one here, let's list that as well. X is equal to pi n, where n is an element of z. All right, so now what they want us to do is use my general solutions to solve between negative 2 pi and 2 pi. All right, so let's start generating some solutions. So what we'll do is we'll go n equals 0 first of all. So let's throw n equals 0 into both of them and see what happens. So I'm going to get x is equal to, so let's put it into this one first. So n is equal to 0, which means that one of my solutions will be 3 pi on 4. Now this is also going to generate some tragically out of order solutions, but I'm going to try where possible to put them in order. N is equal to 0 and the second one is going to be 0. All right, now let's try n is equal to 1. So that's going to be 3 pi on 4 plus pi. Okay, and that pi is going to be 4 pi on 4. So that's going to be 7 pi on 4 as a solution, and 1 is going to be pi. All right, so that is going to be, this is an out of order solution, that's 4 pi on 4, so that's pi. All right, now let's go n is equal to 2. So when we put 2 in here, that's going to be 2 pi, which is 8 pi on 4. 8 pi on 4 plus this is 11 pi on 4, which is more than 2 pi, which means that we've got an out of domain solution. It's more than 2 pi. So n is equal to 2 will produce an out of domain solution for this first one. What about the second one? That's going to be equal to 2 pi exactly. Now 2 pi exactly is also not included because this terminates at 2 pi non-inclusive. So actually n is equal to 2 will produce out of domain solutions. So there's all our positive solutions. All right, let's get our negative solutions now. So what we're going to do is put in negative 1, which is going to be 3 pi on 4 plus, or take away pi. So that's going to be 3 pi on 4 take away 4 pi on 4, which is negative pi on 4. And when I put it in here, it's going to be negative pi. All right, now let's try n is equal to negative 2. So negative 2 is going to be 3 pi on 4 take away 8 pi on 4, which is negative 5 pi on 4. N is equal to 2 here will be negative 2 pi, which is an out of domain solution. So here are all of my solutions. Now let's write them in order. So we've got negative 5 pi on 4, negative pi, negative pi on 4, 0, 3 pi on 4, pi, and 7 pi on 4. All right, let's see how that goes on the calculator. So we're going to go solve cosine 2x plus pi on 4 equals shift root 2 on 2 for x, please, when our domain is negative shift 0, 2 pi less than, remember less than you get from keyboard math 3, less than x less than 2 shift pi. Geez, it almost took as long to type that in as it did to do the problem itself. All right, again with general solutions, with solutions that are negative and positive, the calculator does get some out of order. So let's just check whether we got them all. 0, negative pi, pi, okay, got those ones. But negative 5 pi and 4, which is correct, negative pi and 4, 3 pi and 4, and 7 pi and 4, got them all. Now, I've seen an alternative method to do this problem here, which is to actually do a general solution if that's what you want, and then solve it over the domain like we've been doing. And that's another particular way of doing it, is just to solve and generate a mass of solutions that you think might be between negative 2 pi and 2 pi, and then just chop out solutions that are irrelevant. But I like to use the general solution to produce solutions as well. I think that is a nice, neat method of doing it. Right, so your exercise is 14M, questions 1 to 5.